Okay. Thank you for the introduction. I'm afraid I also don't have any jokes for you. But I'm quite surprised that still so many people show up despite the spring break that is coming. So that's nice. It's a pleasure to be here in Boston and to present my work. So it's something which I have been thinking about for a long time, and I really couldn't make any sense out of it. And then I assembled a lot of different results from different areas, which I found in different branches of literature. And now I think I maybe have a sort of a framework in which one can start some sort of statistical theory around these deep neural networks. And that's what I want to present today. But it's also maybe at the beginning already a sort of a disclaimer that you shouldn't expect too much. I mean, you shouldn't expect the solution to all the questions that arise in the deep learning literature. It's more a sort of a start, and I maybe try to emphasize also what I think is interesting to work on in the future, and where I think there are gaps between the theory and the practical implementation. And it's right, I mean, the computer scientists, they have a head start of a couple of years, and they have invented so many methods and tricks and so on that to analyze all that it would be naive to expect that this can be done within a few papers or so. Okay, so let me get started, and let me also mention I just have 23 slides, so it's, if you have any question, there should also be enough time really to answer any question you have during the talk. So please feel free to ask anything you're wondering about. So I want to start a bit with an introduction, which might not be necessary here, but just to motivate these deep networks. This is the paper here from Krzyzewski and co-authors, which really made this a big topic, and it has, I don't know, 21,000 or 22,000 citations now on Google Scholar. And this is their result, which they report in their paper. So it's about object detection on images. And what you can see, it does remarkably well. So the motor scooter here, for instance, which is almost invisible even by the human eye, it's well classified with this network. And there are plenty of these results, and I could show you many more, where people have really achieved outstanding practical results. But as we know, there's very little theory, and then the question is essentially how to fill this gap and how to start that and how to phrase that in terms of a mathematical problem. Now, so let me just fix a bit the notation, and since I will come back to this later, and this will be important, and I maybe put that on the blackboard so you don't forget about this. So the first one, what we have to pick is an activation function, and so in my talk, that will always be the rectified linear unit. So that's a function from R to R. And here I will take the rectified unit, which is just this function. Okay, so this is now the one which is used a lot in the deep learning literature, and therefore there's a specific interest in just analyzing this activation function, and maybe I later comment a bit on how to extend it to other activation functions. Now, what we else need is this to pick. We need to pick a network architecture, and here this is two numbers. The first one is a positive integer L, which is somehow the number of hidden layers, and the second one is a vector P, which is the vector of length L plus 2. Okay. And once we have done that, we need to fix one more notation. And this is what I have written here. I just want to explain it to you what it is. So if you have two vectors, let's say y r-dimensional vectors, then sigma v of y, that just means somehow we take the vector y, we subtract v and then we apply the activation function component-wise. So it's y1 minus v1 applied to sigma, and okay, so that is what it means. And if we have done that, we can write a neural network with this architecture LP. We can write it in this form, where we think about this as something where we start from the right and then we compose these operations as follows. So we first have an input vector x. We apply this x to a matrix W1, and that gives us another vector. And then we do the shift by V1, and we apply component-wise the activation function. That is still a vector which we can then apply to a matrix W2. And we just continue, and we do that essentially L times. And then finally, we apply once more a weight matrix WL+1, and that is our network function. And these three parameters in this class are these weight matrices Wi, which are pi times pi minus 1. So this is where the vector p goes in. And the vi's, the shift vectors, they're also three parameters. And those are the ones which we can, for instance, use to estimate the underlying function. And something which you should see here is that there, for instance, to represent one function with these networks, if you have, for instance, one representation in this form, there are plenty of other representations. So it's really hard to classify the equivalence classes in terms of the parameters, and it's somehow, I think it's an infeasible problem to do that. And so there's no way to work with these weights directly. So the only thing you can say essentially, you cannot say anything about the weights, but you can say something about the functions, the network functions. Okay, and so the way these networks are introduced in the literature is more these graph representations, where you get an input vector, and those are the components of the input vector, and then you see somehow how this input vector somehow flows or goes through this directed graph, and the nodes or units are arranged in these layers, and each unit stands for a scalar product of the incoming signal with the weight vector, which is shifted by a number and applied to the activation function. Okay, and what you should see is that this definition from the previous slide and this one here, this one and the one with the graph representation is exactly the same thing, where this number L on P, okay, so L on P is just nothing else than, so L is the number of these hidden layers in the network, in this case 2. And the P, which you have here, this width vector, is just the number of units in each of the layers. So it's the input layer has 4 units, then 3, 3, and 2. So it's 4, 3, 3, 2. Okay, and so it's just an equivalent description. But it's much nicer to think about networks in terms of vector matrix multiplications than in terms of these graph representations. I think they're not really useful for doing mathematics. Okay, so far, what type of theoretical results are there for these deep networks? So the first one, which is also the oldest one, is about the expressive power of deep networks. Okay, so or the approximation theory, if you like. So that really starts in the early 90s, when there was, in the late 80s there was the backpropagation proposed, and then in the early 90s there were some theoretical results. And the first ones were essentially that a shallow network, so a shallow network is just a network with one hidden layer. If you make the number of units if you add units, you can essentially approximate any continuous function up to an subnorm error of size epsilon, and then just the epsilon depends on the number of units that you have to pick. Okay, so that means somehow even already the shallow networks, they are dense in the class of continuous functions, and then this poses, of course, the question, so why should you add then additional layers if this is already a class that can approximate anything? And that has something, of course, to do with the rates of approximation that you can achieve. So the shallow networks are not very good for certain things. And so what people have now figured out is so there are some results which say, for instance, okay, this function I can approximate with much less parameters with 2 hidden layers than with 1 hidden layer. So we have few results of this type. But lately it has been, for instance, also been shown that certain things like just multiplication is much easier to do with multiple hidden layers than with just 1 hidden layer. So you can think, if we go back to this formulation here, suppose you get this, what you want to construct a network. You get as input x and y, and you want a network function that approximately outputs x times y. And then you can see, of course, that it's not very easy with such a structure with just multiplications with matrices to approximate such a function if you just have one layer. And there are certain tricks which you can use in order to do that much more efficiently with few parameters if you have several layers. Okay, so this is a bit about the existing approximation theory. It's actually quite rich, and there's a lot is developed at the moment as well. And then for the statistical risk for deep networks, you just interpret a deep network as a statistical method which gets data and estimates some quantities or predicts something. There's quite little, so there's now more. For instance, Sasha has some work on for instance, the bounds on the BC dimension or Rademacher complexity, and so. But in terms of, like, let's say, rates of convergence, there was very little, and that is something I will talk about today quite a bit. And then other areas where there has been some theory is about some people have worked on the stochastic gradient descent, for instance, questions related to how to escape saddle points. And so on, and there's some theory about that. Another thing which I believe is quite interesting, and I also will come back to that later, is about the loss surface or the energy landscape of these networks. So there are many local minima and maybe also saddle points, and then the question is how they are arranged and how do they look like, how can we characterize them. And finally, something which is also quite new is about what you can do is essentially you can go to some sort of continuous limit if you take the number of hidden layers to infinity, and then you get to some sort of interpretation of a deep network as a dynamical system, and you can use theory from dynamical systems to analyze these networks, and that is another direction. So you see there are different directions, maybe there are even more than I have mentioned here, and I just want to talk essentially about the statistical aspect, and in the end, I think maybe one would like to combine all of these things together. But I should mention, I mean, I don't believe that there's somehow the unifying theory of everything or so for these deep networks. I think it will always stay in the sense that people look at different aspects. So there's too many things to be analyzed, and it's too complex as a method probably to come up with a somehow satisfactory theoretical solution to everything. Okay, so what we want to do if we try to do a statistical approach, what we want is really we want to model the networks and the problem as realistic as we can, given what is done in practice. Okay, so what we want is essentially to take all these characteristics that we have in practical applications and that are typical for these networks. We want to take them somehow into account. And so I just want to mention a few of them here. The first one, the networks are deep. Okay, so that is, everyone knows this, of course. But one important thing is that they also become somehow deeper over time. So I don't know, 3-4 years ago, it was 23 layers, and now it's 152 layers, and it will be more, or it's already maybe more than that. And so it's really growing over time. And the point I want to make maybe later also is a bit that this, from this type of theoretical result that we have, one can maybe interpret this as a sort of big data phenomenon, in the sense if you have more data, you should also take a deeper network. But we will come to that later. Another point I want to make is that for statistical modeling, you should take networks where there are more parameters than your sample size. Okay. So as an example, I have this AlexNet, and also this plot which I took from this article here. And in the AlexNet you have about, so the size of these balls corresponds to the number of parameters in this network, which means all the entries of the weight matrices and the shift vectors. And so you have about 60 million parameters here. But for that one, you just have 1.2 million training data. And this is the one I showed you in the beginning with the image classification results. Now, if you have some sort of noise-free problem, then you might, of course, just interpolate, and then you can also overfit and everything. But if you do something statistically and you want to include measurement noise, and so you need some sort of regularization. So there's no way you can do, for instance, regression, what we'll consider later, without having some sort of regularizing principle. And so this is, I think, where also the approach that we have differs from what is done in practice. So what we just say, well, to avoid the overfitting regime, we just assume essentially that the true networks are sparse, and we fit a sparse network to the data. This is not really realistic. So you can see it's like specific network architectures, like the convolutional neural networks, which are used for the AlexNet. They have a sort of sparsity because you take these patches also, which are local. So you have the weight matrices. They are tuplets in this case, and they are somehow banded tuplets matrices. So there are lots of zeros in these matrices. But it's not exactly the same type of sparsity that we consider here. So there's, I think, a lot of room for improvement. And finally, what is important, and that is also very different to what is done in, for instance, in the literature in the 90s, is really the rectified linear unit as activation function. That is something you want to analyze. Okay. Now there's another thing which I want to mention, because it's in the approximation theory, it's maybe a bit sometimes, what people do, or even if you look at the very old results about the universal approximation theorem, you see that the results of this type, you have to take some of these parameters extremely large and maybe some of them very small ones. So, okay, and then you can approximate any function. Okay, but this is not really what we observe in practice. I mean, I also have made some experiments, and you don't have that the fitted networks. They have like network parameters 1 million or 20,000 or so. Typically, they're quite small. Okay, and so therefore you don't want to allow that if you really want to model that realistically. And so I can show you what happens. So what I call this large parameter trick here is, for instance, if you take this rectified linear unit and you multiply the input by a, and then you subtract that, you get essentially this blue curve. And the blue curve, then you can approximate, if you make the a very large, you can approximate this perceptron activation function arbitrarily well. And from the approximation theory, you can make then a lot of claims and play many tricks. But I think it's not very realistic. So what one needs, I think, is a sort of constraints on the size of the parameters. And there are many things you can imagine to do that. One thing which we have done is very simple. We just say, well, we work with networks where all the network parameters are bounded by 1. Okay, and that is really also something which later goes into these results about which depth you should take. If you would not have such a constraint, you can take networks which are not as deep. Okay, so then we want to do statistics for that, and just you can ask, so what type of problem you want to look at, and something which is maybe the most convenient one to work with, because it has been studied so extensively in the literature, is just you say, well, let's study the nonparametric regression problem. Okay, so what we do is we just assume we have our training data or our data just IID copies from the nonparametric regression function with regression function f, which is goes from RD to R. And we can compare it essentially with, for instance, the rates with other methods like kernel smoothing methods, wavelets, and other things. Okay, now what is somehow the statistical estimator? Here we just say essentially we pick the network architecture. Okay, that will be the L and the width vector P, and we also pick the number of active or non-zero network parameters, which is denoted by little s. Okay, so I mentioned before somehow we just say somehow that the network might be very large, but the number of non-zero parameters is maybe much smaller. And then we just consider as a first approach towards this area just plain empirical risk minimization. Okay, and this means somehow we minimize the least squares loss, the empirical least squares loss over this function class. So also in the deep network literature, you take typically the loss that is induced by the log likelihood of the problem. In this case, it's just the least square, so that matches. But then we take somehow the global minimizer over the whole class, and that is of course you cannot even compute it, but you can study it as a theoretical object. And then we are interested, let's say, in prediction error, and we want to study the prediction error in the statistical or non-parametric statistics framework. Just want to know, like, how fast does it, if I increase the number of samples, how fast does this scale towards 0 in terms of the rate of in n. Okay, so the big thing is, of course, this global risk minimization thing here. And then the question is, how is that realistic, right? I always want to make the problem, the point, and in the end you want to model everything as realistic as possible. So, and what I maybe want to mention here is some interesting work about the loss surface, okay? Because something which you can do, of course, always, it's a very easy relaxation of that. What you can say is, I don't take the global minimizer, I just take any network where the loss of the network is bounded by the global loss plus some, let's say, delta n. And then, as you know, you can extend this typically that the delta n that you have here goes then into the rate of convergence. If you're very far away with your loss, that will induce, of course, a large extra term into your rate. If you're very close to the global loss, it will not matter. And there's some heuristic about this energy landscape, and that goes back to this work by Koromanska and co-authors, and they make a link to these spherical spin glasses. And what they claim, and this is just so it's not proven, it's not rigorous, but somehow quite a nice heuristic that you can link these loss surfaces to the Hamiltonian of these spin glasses, because those Hamiltonians have been studied, and it's known somehow that all the local minima they lie in a band. Okay, so you have this. Let's say this is the global minimum here, and then you have all the local minima. They lie somehow in a band, which is of course lower bounded by the global minimum, but they can control somehow the size of the band. Okay, and so what the band is essentially proportional to the geometric mean of the width vector of this P here. And that means somehow that tells you at least all these local minima lie in this band, and this is essentially something, if you could make this heuristic rigorous, you could add that here to this global loss, and then you can, for instance, treat that in terms also of the rates of convergence, but at that moment, it's just a heuristic. Okay, so just to give you an idea about what the problem is. So we want to fit a network to the non-parametric regression problem. And if you just think about shallow networks, right, networks which have one hidden layer, then this is the same as saying we want to fit functions of this form to the non-parametric regression data. And these functions, you can see them somehow, those ones you can view as a sort of basis functions, okay? And those are the coefficients, and many of these classical basis expansion problems in non-parametric statistics, they just are interested in getting the coefficients right, but here we also have somehow the choice of choosing the AJs and the BJs, so somehow we have bit of flexibility in the basis, and that is also known as a dictionary learning problem. But this is just in the one-dimensional case, and if you have multiple layers, you have much more flexibility in how to choose the regression function. Okay, so another point is, what type of function class should you consider, right? What is now the right class to model good functions for which neural networks perform well? Start would be just to say, well, I assume my regression function is a beta smooth function. And for this, it's well known what the best possible rates are that any method can achieve is the prediction error rate would be then n to the minus 2 beta over 2 beta plus d. And that is somehow dependent on this curse of dimensionality. If you make the d large, and the d will be typically large in these neural network applications, this rate is very slow. Okay, so it converges very slow. And my point is a bit results which are on this function class. It doesn't matter whether neural networks perform well or not, because that cannot be the right class. Any method, if that would be the right class to consider, then any method would perform very bad, and there would be probably not results of that quality. So the thing is, you really want to make a good structural assumptions on the regression function, which allow you in the end really also to get faster rates, and also to have something where you can believe that is something where neural networks can indeed perform better. And so the idea is, here's a sort of a heuristic of our idea when this happens, is that somehow one can believe, and that is so also we put that in the paper just as a side remark. For instance, to Marshall Pocho, he sent me an email. He just mentioned that they also had something in one of their articles. So it's always nice to see that other people were also thinking about this. And this is, but just let me maybe explain it here. So the idea is that one can believe that neural networks perform well in cases where you have a sort of modular structure in your underlying object. Okay, and what do we mean with the modular structure? It means somehow that you can build complex objects from simpler ones in an iterative way. Okay, so for instance, here this sentence or so. You can essentially think about this. You first build lines, and from the lines you build letters, and from the letters you build words, and then sentences and paragraphs and so on. So you have this type of hierarchical or modular structure. And that is something where, for these type of tasks, one can believe that the neural networks perform good. And one thing which is really I think, which is maybe also new in what we do, is that if you go from one hierarchy to the next layer of abstraction, you don't include everything which you have built at that moment into the next layer. Somehow you take a sparse selection of these objects into the next one. So you don't build words with all the letters that you have, or a sentence with all the words that you can build or so, right? You take a few words for one sentence, or a few letters for one word, and so on. So there's a sort of sparsity, and that is what we want to model. And how does that look then in terms of like functions? It's exactly this. We just say, maybe I put that on the blackboard as well, because we need it later. We just say, well, we believe that our regression function is a composition of other functions g naught to till gq. So we have a function g naught, and then we compose it with g1 up to some gq. And the gi is just a function from di to the di plus 1, and d naught is just the input dimension d, right? And now this function gi, they have di components, or di plus 1 components. And so what we now impose is that these functions gij, they have smoothness beta I, and they only depend on ti variables. Okay, they do not necessarily depend on all the variables that you have at this stage. They just maybe depend on 1 or 2 or much less. And so the Ti will always be bounded by the Di, right? That's the maximum. But you should think about as being Ti being much smaller than the Di. Okay. And that is exactly what I try to motivate with the last slide. Somehow if you go to the next deeper layer of abstraction, you somehow take a few objects from the last layer and combine them in a nonlinear way into something new. And now everything, so you can, if you like, you can forget about the structure. Everything that you have to remember is that the definitions of the Ti's and the beta i's, that is really what shows up in the rates of convergence later. And you also should not confuse that with the network. So this Q, for instance, has nothing to do with how we choose the number of layers in the network. So this is completely unrelated. It's just a structure assumption on the regression function f, and it has nothing to do with networks. So. But it's, of course, something which very natural also for networks to make such an assumption. I also should mention that there's many different or similar or so type of structures have been studied, for instance, in papers by Enno Mammen, where they iterate between functions and summation, and then by Kohler and co-authors, where they do something similar. There's one paper by Zyberkov, Yuditsky, and Lepsky, where they study the case Q equals 1 and minimax estimation rates for them under subnorm. And so this is it has been somehow considered a bit also in this non-parametric statistics literature in different ways. Okay. So now I want to give you a specific example. Those are additive functions which have been studied a lot in non-parametric literature. And in an additive function, we just assume that the regression function is the sum of the individual components, and then somehow somehow functions of the individual components and summed up. And we can write that in this form. I will explain you in a second why this is useful. We can write this as G1 composed with G0, where G0 is just the function which maps RD to RD by making a vector, and they're somehow of one-dimensional functions. And the G1 is just the summation over the functions from the G0. Okay, so you just sum them and then you get that. Okay, and if you write it in this form, you can see that now the T0, right? This is just 1 because in G0 everything just depends on one variable, and the T1 will be D because everything. So this depends on all the variables. But this decomposition is quite useful, and because those are these two scenarios where we can get faster rates than the ones which are typically induced by the curse of dimensionality. Because in this setting, in this first setting, we have one-dimensional functions, so it's somehow not affected by the curse of dimensionality in terms of that it slows down the rate in n. And the second function is it depends on all the variables, but it's infinitely smooth. Okay, so therefore we also get fast rates for that. Okay, and that means if we can get fast rates for these two components, you can believe, of course, that you also can get fast rates for the composition of that. So it makes sense somehow, and it's just a special case essentially of this framework additive models or generalized additive models and many other things. Okay, something we also have to do before we can state the rates is what matters for non-parametric regression, namely essentially the smoothness on the function f. Okay, if you the rate of convergence is essentially determine how well you can separate the noise from the regression function. This is determined by the smoothness on the regression function f. And if we put the smoothness on these GIs, which are in this decomposition, then we have to ask the question essentially, what smoothness does that induce on the function f? Okay. And this is what is here written down as or mentioned as effective smoothness. You take the smoothness of the function that is here in the GI, function. And if you now pass this function through the higher abstraction functions, then the smoothness can deteriorate. And essentially, this is the factor with which it can deteriorate. Okay, so if you take a function, something like x to the alpha, which is alpha smooth, and you compose it with x to the beta, then you get something like x to the alpha beta, and then you get something which has smoothness alpha times beta. So you see that this type of multiplication makes sense. If the functions are more than Lipschitz or more than Lipschitz, which come in deeper layer, the smoothness does not change anymore. You can just see that with the triangle inequality. Yeah.
So the smoothness controls the quality of approximation in a regime where the dimensions are fixed and the sample size goes to infinity. At the beginning, you suggested that we're interested in a regime where the sample size could be much smaller than the number of parameters and so on, in which case it would be even worse quality of approximation, right? So
yeah.
I understand you control it by sparsity, but on top of sparsity, there's probably entropy of the choices where to put those sparsity, right?
Yeah, so this is now this assumption on the regression function f, which we have. And we assume, ideally, what we would like to do is we would like to take the input dimension d to be very large and maybe also growing with n. At the moment, it's fixed, but you can see it view it as being large. And then there's this other story with the network where we say, well, we want the number of network parameters potentially being large, and that is still true. I mean, we didn't change that. You will see that it will come in on the next slide. Yeah. Other questions? No. Okay, good. Let me then show you this result that we have. It has 3 conditions, and those are the 3 conditions on the network that we fit to the data. Okay, so the first condition says, and I will discuss them later in more detail. The first one says take the L, or the depth of the network, take it proportional to log n. Okay, so that means somehow if the n is the sample size, and you should scale it with log of the sample size. And the second one is that the width of the network should scale like n to the power c, with c larger or equal 1. But you can relax that essentially if you look into the paper, but I didn't want to spoil you with too many technicalities here. You can relax it to much wider class of networks. But for simplicity, just think about the width in each layer being n. So you take n units in each layer, so quite a huge number of units in each layer. And the third condition is the crucial assumption is, namely the network sparsity, that has to be of the right order. Okay, so the network sparsity, that really depends also on these numbers ti and beta I star, which you typically don't know, so it's the like non-adaptive case. And if these 3 conditions are satisfied, then you get for the prediction error, you get the rate of convergence which scales like n to the minus 2 beta I star over 2 beta I star plus di up to this log squared n, which is suboptimal. And this is somehow if you compare to this literature in nonparametric statistics, this is the classical nonparametric rate with slight changes, namely the beta I stars and the ti's. So you have the effective smoothness instead of the classical smoothness here, so the beta I stars, and the ti's, which can be much smaller than the di's, as I mentioned before, somehow the effective dimensions here. And that might give you then faster rates. So here are some comments on the rate of convergence. The first one is that the ti's are what I mentioned, the effective dimensions. And the second one is actually we have a proof that this is also the optimal rate up to log squared n, but it's not in the paper yet. And finally is that other methods, like suppose you do non-adaptive just wavelet estimation. Okay, you take a wavelet expansion and you just take some of these wavelet. If the wavelet coefficient is large, you take it into the expansion. If it's small, you replace it by 0. And these estimators, they do not achieve these rates. Okay, why don't they achieve these rates? Because this assumption on the regression function that it's a composition of other functions, this nonlinear structure, wavelets do not see that. So you cannot see that back in the wavelet decay. And therefore, if you have such a structure on the regression function, somehow you don't get the optimal rate. You will get essentially you get here the DIs instead of the TIs. Okay. Okay. So now about the assumptions on the network architecture. The first one is that the depth should scale like log n, and this is something which is really natural in these proofs, and that comes because of something. Maybe I will shift that to the next slide. One thing which you really should see is that here we have some scaling where you make the network deeper if you have more data. Okay, so if you have a network and that fits well, and someone gives you maybe twice as many or 10 times as many data, maybe you should take a deeper network. That is what it says essentially. You should always see that in the framework of the specific problem that we consider here, of course. Okay, if you think about a different problem, if you want to do something where I don't know, like object detection on images, which is more like random deformation of objects, might be something different. Okay, so but in this specific case, I think it's the right scaling of the network depth. Another thing is, and now I come back to your question, is the number of network parameters can be much larger than the sample size. Okay, so what is the number of network parameters that we have? Is the width, the number of units is n to the c, and then those are pi times pi minus 1 matrices, so it's n to the 2c, so it can be, for instance, n squared or so. And then you have log n layers, so it's log n times n squared. So you can have much more parameters in your network than your sample size. Okay, but what matters is that you get the network sparsity that you need to get of the right order. Okay, so or otherwise, what you can say is take a large network but regularize efficiently, and then you can get good results. That is essentially what the claim is. So the L on the P you can also pick independently of the underlying parameters that are induced by this structure assumption on the regression function f.
But with the sparsity, it's a fewer number of parameters than n, right?
Yep.
So the effective number of parameters is smaller than the sample size.
Yeah, exactly, yeah. So this will always be smaller than n. Here, this one, yeah, obviously, yeah.
So it sounds like TIs, you can afford to take at most something like log n over log n or something like that. It should be very slowly growing function of n in order for this bound to make.
Yeah.
Right?
So the TIs are given to us, right? I mean, somehow they are in this function composition. We don't know them or typically, and that's a bit the thing here that we don't really know how to choose that of which order, and we want them. We would like them to be very small because then we get fast rates here. So that's
so
the point.
Think of them as fixed, and then
exactly, yeah.
But this bound suggests that even if TIs are slowly growing with n, this
then
still could be useful bound as long as it's very slowly growing, like log n. Or
maybe,
log
yeah,
n over log n.
Okay, so here's something else which I find quite interesting about that, and this really comes also partially from this existing approximation theory, is that you can get good rates for all smoothness indices beta I or beta I star. And why is that a paradox? So if you think about nonparametric methods, for instance, if you take a nonparametric estimator that is based on piecewise constant approximations, then you can go typically up to smoothness 1, and if you're more than if you're more than Lipschitz, then the piecewise constant approximation is not good enough anymore. So you need too many parameters to parameterize a signal which is 10 times differentiable or so. Okay, so therefore you immediately don't get good rates anymore for smooth objects. If you take something piecewise linear, typically with all the methods that we have, linear spline methods and so on, you can go up to smoothness 2, and then you have the same problem. It's not the approximation theory is not good enough anymore for higher smoothness. But here, what you can do is you really don't have any constraint on the beta I, although the the deep networks with rectified linear unit, they always produce piecewise linear functions. So if maybe I should go back and explain that in more detail here. So this function here, if you take sigma being the rectified linear unit, this will always be a piecewise linear function in the input x. Okay, and we use that for approximation and fitting to the data, and so it's quite natural to think more than 2 times differentiable functions, they cannot be efficiently approximated, but they can. And that has something to do with the nonlinearity of this class. And what I want to claim here is really that this nonlinearity is very helpful and it's very essential. And this is essentially also what drives this network depth log n. So if you would take a network which is shallow or where the depth does not grow that fast, you would not have this effect that you can approximate smooth functions that well, and then you lose a bit in the result. Okay, finally on the proof, last 2 minutes of my talk. The first one is the classical type result which you can obtain for empirical risk minimization. The first one is an Oracle inequality which decomposes the problem into an approximation problem plus something which accounts for the variance. And in the variance, the important thing is that it scales with the network sparsity S log. And then the log n essentially is due to the network depth. Assuming here already that the network depth is of order log n. And then the tricky bit, or the more, where you have to invest even a bit more technical work, is the approximation theory. You want to bound this thing. And here there's a lot of interesting results by starting with work by Tchaikovsky, and then there are other people who built on that, Liang and Skrikhan, but also a very nice paper by Jarotsky. And I have used these results essentially, and I have further extended them for 3 more things, I believe. The first one is that right at the beginning I said we don't want to do the large parameter trick, so we don't want that parameters can be arbitrarily large. So that induces some extra technicalities here. Secondly, what they do is typically they show that there's one network architecture which has certain approximation theoretic properties, but here we want a large class of network architectures for which we want to have that. It's a bit a different type of question. And we also want essentially the dependence on all these quantities, the Ti's, the beta i's from the function decomposition, the network sparsity. We want to see that all in the rates. And therefore somehow we need to work much more explicitly with these expressions. And finally, we also have somehow non-asymptotic results for the approximation theory, which I believe are very helpful also to continue with these type of results. Okay, so on my last slide, I just want to come back to this additive model, and then I stop. I mentioned that you can decompose the additive model into these 2 functions, G0 and G1. And if you do that, then as a direct corollary of the general result, you get that in this case you obtain the prediction rate n to the minus 2 beta over 2 beta plus 1 times log squared n. This is something due to the proof, or also maybe due to the network, but it's just a logarithmic factor. And this is essentially known to be the optimal rate that you can achieve for additive functions. And therefore, you see somehow many of these structural constraints that have been studied in the literature, like additive models or generalized additive models, and so they are all here special cases, and you can get from the main result, you can get corollaries, and you typically see that you achieve the good rates, which then do not depend on the curse of dimensionality anymore as a special case of the main result. And another thing which we have, which is maybe new, is a sort of sparse tensor decomposition. So if your true function can be written as a tensor decomposition with very few non-zero coefficients, then you can also show that you can get very fast rates for that. And you don't need to know the tensor basis, which I think is the interesting bit. Okay, so let me stop here. Thanks for your attention, and maybe you have questions.
Classification problems where these things are being there's somehow the decision boundary, right? How well you're approximating.
Mhm.
If you're on the right side, then you're done, right?
Yeah, yeah.
So you can have natural assumptions, like the typical Hierarchical paper where rates are fast.
Mhm.
Have you thought of using these techniques in conjunction with that?
Yeah. So I mean, one natural way is to how you can extend the regression to classification is you just essentially you take the regression function and then you classify based on that, and then the result, for instance, in the book by Lugosi and so. And that you can do. It's more or less straightforward. Something which is more interesting is probably you want to include the softmax function as a last activation function on the last layer, and it's something which we also have done. But what you mentioned, I think, with these fast rates in this context, it's not. We haven't really looked at this one. Yeah.
So I have a small comment that I think one cool thing you can do is let's assume that all the functions have the same beta i's and the same ti, like 2, for example.
Mm-hmm.
Right, and then using and then let's also take for granted that Google's inception before is already optimal, right? So then that it has the right sparsity, right? So then you can maybe use that sparsity that they achieved to infer what's the betas and what's the beta and t for the functions that they're eating.
If you believe that this is the right thing, yeah.
That would be fun,
It's
because that would be a result
yeah.
of nature, like, okay.
I'm always a bit critical about estimation of the smoothness index, so that is considered to be a very tough problem or even unsolvable problem in nonparametric statistics. But you could, in principle, try something like
If
this.
plenty
Yeah.
networks give you all the time the
It's
same
a,
result,
maybe it's a sort. Yeah, yeah. Could be something like this. Yeah. Interesting remark.
Any other questions?
Okay. Thanks. Yeah. Mhm.